Good morning to one and all present here. We are Group 2. Our topic is DRAM. In the group, we have Aaryan, Aayush, Atish, and I, Janhavi. Next. Let's start with what DRAM is. DRAM stands for Dynamic Random Access Memory. It's volatile, meaning all data is lost when the power is off. It stores data as electrical charge in a capacitor and transistor, but since charge leaks, it needs refreshing. That's why it is called as dynamic. Despite this, it's everywhere because it balances speed, cost, and density very well. Perfect as a computer's main memory. Next. Now let's understand why DRAM is such a big deal. It's the backbone of modern computing, fast, reliable, and compact. Compared to SRAM, it's slightly slower, but much cheaper and offers high capacity. Over the year, it's evolved from SDRAM to DDR5, improving speed and efficiency. Today, DRAM powers PCs, smartphones, servers, and GPUs, handling multitasking and fast data easily. Even with new tech, DRAM isn't going anywhere soon. Next. Now let's have a quick comparison of SRAM and DRAM. SRAM uses flip-flops, while DRAM uses a transistor and capacitor pair. Both are volatile, but SRAM is faster. DRAM is much cheaper and denser comparatively. SRAM doesn't need refreshing, while the DRAM does. SRAM is mostly used in computer cache, while the DRAM is the main memory of the entire system. Power-wise, SRAM consumes more, even the ideal ones. The DRAM is low power, though the refreshing pass adds a little bit to it. So the SRAM is equal to speed, but the DRAM is equal to balance of about affordability, efficiency, and the perfect for everyday use. Next.
So starting with the basic DRAM cell, which is also called as a 1T1C cell, each bit of data is stored using one transistor and one capacitor. The word line controls the transistor while the bit line carries data. A charged capacitor means logic 1 and a discharged means 0. Since capacitors leak charge, DRAM cells must be refreshed regularly. Cells are arranged in rows and columns. Rows are connected by word lines and columns by bit lines. Each row's data is stored in a row buffer, and DRAM chips are divided into multiple banks to allow parallel access. Accessing the same row is fast, but switching rows adds latency. In read operation, bit lines are first pre-charged to a mid-level voltage. Then the selected word line activates the row connecting cells to the bit lines. Sense amplifiers detect the small change difference and amplify it to the fully logical levels. The column axis then sends the data to the bus. Since reading disturbs the charge, the data is immediately rewritten, and the row is pre-charged again. Burst mode allows multiple words to be read in one go for higher speed. In a write operation, the row is activated just like in a read. The controller drives the bit lines with new data, and after writing, precharge closes the row. During refresh, every row is periodically reactivated and precharged to restore lost charge and maintain data integrity. This happens automatically without using the data bus. Finally, DRAM performance depends on timing, reliability, and power. Delays like TRCD, TRP, and TCAS define access time. Row buffer hits are fast, while conflicts are slower. Reliability issues like the row hammer effect are handled by ECC, and higher temperatures increase leakage, requiring faster refresh. Power use is roughly 40 to 50% active, 30 to 40% refresh, and 10 to 20% idle. As DRAM scales smaller, leakage rises, pushing innovations in materials and designs.
Let's begin with the heart of computer memory, the DRAM architecture. At its core is one T and one C cell, meaning one transistor and one capacitor. The capacitor stores a single bit as electrical charge. Charge means 1, discharge means 0. Since these capacitors leak over time, the data must constantly be refreshed, which is why it is called dynamic RAM. These cells are arranged in grid of rows and columns, allowing billions of bits to be stored compactly. The memory controller manages this grid, translating the computer's request into signal that read or write specific locations. Next, Now, how do DRAM access a single bit among billions? It follows four key steps. First, RAS. The controller activates an entire row and loads it into the temporary buffer. Second, the CAS. It then pinpoints the exact column for the required data. Third, for a read operation, the sense amplifier detects the stored charge, and the write operation, the new data changes the charge. In pre-charge, the row is closed and made ready for the next access. Meanwhile, the refresh cycle quietly runs in the background to prevent data access. Next, talking about the types of DRAM, DRAM has evolved through many generations. Early types like FPM and EDO paved the way for SDRAM, with synchronized memory operation with the system clock, which is a major speed boost. Then came DDR SDRAM, double data rate, which transfers data twice per clock cycle. Over time, we have advanced through DDR2, DDR3, DDR4, and now DDR5, each offering faster speeds and lower power consumption. For mobile devices, there are LPDDR, which stands for low power DDR, optimized for energy efficiency, making it ideal for smartphones and tablets. Next,
So now let's talk about the advantages and limitation of a DRAM. DRAM offers high density, low cost, and a compact design which makes it perfect for storing large amount of data. It's widely used in devices like PCs, servers, mobiles, and GPUs, and keep evolving with advanced versions like DDR4, DDR5, and 3D stack DRAM for better speed and performance. However, it does have some drawbacks. It needs frequent refreshing, is slower than SRAMs, consumes more power, and it volatile, meaning data disappears once the power is off. Next, in real life, DRAM is used almost everywhere. It is the main memory in computers and laptops. Helps GPUs handle high-end graphics, power servers, and data centers for cloud computing, and even supports medical devices, IoT systems, and aerospace equipments. Next,
Now let us look at where it stands in today's modern scenario and what lies ahead in the future. Talking about the modern scenarios, DRAM underpins AI, gaming, and high performance computing, fueling cloud servers, GPUs, and data centers with rapid data access. Advanced variants like DDR5 delivers superior bandwidth with high energy efficiency, while the HBM accelerates the AI and GPU workloads. Let's look at the future scope. Emerging 3D stack and non-volatile DRAM promises a high density, speed, and persistence. Integration with AI and edge computing will optimize real-time performance. Alongside ongoing innovations are the two main innovations that are one minimizing the refreshing power and the second one is minimizing the energy efficiency. Next. To conclude with, the DRAM remains the bedrock of contemporary computing, continuing to evolve. The urgency of AI, emerging gaming, data intensive prodigies, and high end data involvements. With innovations in velocity, efficiency, and seamless integration of the power, this can be the most important technological impact in our society. Thank you.